Welcome to this lesson on beta decay, specifically focusing on electron emission. Beta decay is a fundamental process in nuclear physics where unstable atomic nuclei undergo transformation. In this lesson, we'll explore how neutrons convert into protons, what beta particles are, and how this process works at the nuclear level. Let's dive into the fascinating world of radioactive decay. Beta decay is a type of radioactive decay where an unstable atomic nucleus transforms by emitting a beta particle. But what exactly is a beta particle? Beta particles are high-energy, high-speed electrons, or positrons, that are ejected from the nucleus during this decay process. It's important to understand that even though electrons are being emitted, they actually originate from within the nucleus itself, not from the electron cloud surrounding the atom. Let's look at the beta-minus decay process in detail. In this type of decay, a neutron inside the nucleus transforms into a proton. But that's not all. When this transformation occurs, two particles are emitted: an electron, which we call a beta-minus particle, and an electron antineutrino. The neutron essentially splits into these three components: one proton that stays in the nucleus, one electron that shoots out as the beta particle, and one antineutrino that also escapes. This is how the nucleus changes its composition. The nuclear equation for beta-minus decay follows a specific pattern. We write it as a subscript Zx transforms into a subscript Z plus 1y plus E minus plus new bar subscript E. Let's break down what each symbol means. A represents the mass number, which remains unchanged during the decay. Z is the atomic number, which increases by 1 because we're converting a neutron into a proton. X is the parent nucleus, Y is the daughter nucleus. E minus is the beta particle or electron, and new bar subscript E is the electron antineutrino. Notice how the mass number stays the same, but the element changes because the atomic number increases. Let's examine a real-world example, the beta decay of carbon-14. Carbon-14, with mass number 14 and atomic number 6, undergoes beta-minus decay to become nitrogen-14, with mass number 14 and atomic number 7. During this process, an electron and an electron antineutrino are emitted. Notice that the mass number stays at 14, but the atomic number increases from 6 to 7. This means carbon transforms into nitrogen. This is the same carbon-14 used in radiocarbon dating to determine the age of ancient artifacts. Beta particles have several important properties. First, their identity. They are high-energy electrons emitted from the nucleus. Their mass is the same as any electron, 9.11 times 10 to the power of negative 31 kilograms. They carry a negative charge of -1 elementary charge, but here's what makes them special: their speed. Beta particles can travel at incredibly high velocities, reaching up to 90% of the speed of light. This high speed gives them significant penetrating power, though they can still be stopped by a few millimeters of aluminum. Energy plays a crucial role in beta decay. The decay energy, also called the Q value, comes from the mass difference between the parent nucleus and the decay products. This mass is converted into kinetic energy according to Einstein's mass-energy equivalence. This energy is shared between the beta particle and the antineutrino. All conservation laws are obeyed. Energy, momentum, charge, and lepton number are all conserved. The antineutrino carries away variable amounts of energy, which is why beta particles don't all have the same energy. Instead, they show a continuous energy spectrum, ranging from 0 up to a maximum value. Let's summarize the key points. First, beta-minus decay converts a neutron into a proton, emitting an electron and an antineutrino in the process. Second, during this decay, the mass number stays constant, but the atomic number increases by 1, meaning the element changes. Third, beta particles are high-speed electrons that can travel at up to 90% the speed of light, giving them considerable energy. And fourth, the decay energy is shared between the electron and antineutrino, creating a continuous energy spectrum rather than discrete energy levels. Understanding beta decay is essential for comprehending radioactive processes, nuclear stability, and applications like medical imaging and carbon dating.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.